Welcome back for another deep dive. Today we're tackling something really mysterious, dark matter. But we're going beyond the usual, what is it question. We're going to explore what dark matter might actually do,
Yeah.
based on some fascinating research.
It's a shift from thinking of dark matter as just some inert substance to considering it as a dynamic force shaping the universe.
Right. Our source material is a 2008 research paper from Caltech. It's titled Dark Matter and Dark Radiation. And it proposes something really wild. Uh, what if dark matter has its own forces and interactions, a
hmm
whole hidden world
Right.
operating alongside our own?
The paper focuses on the idea of dark electromagnetism, a force similar to the electromagnetism we experience, but acting only on dark matter particles.
Okay, so let's break this down. We know dark matter exists. We see its gravitational effects on
Yeah.
galaxies and clusters of galaxies. But we don't know much about what it actually is.
The standard view is that dark matter is made of particles that don't interact much with each other or with regular matter except through gravity. They just sort of clump together under their own gravity.
But this paper suggests that dark matter might be much more complex.
Yeah.
The researchers introduced the concept of a dark photon,
Right.
a particle that would carry this dark electromagnetism force.
It's like the photon, the particle of light that carries the electromagnetic force in our world.
Okay.
But it exists solely within the dark matter world.
So instead of being a bunch of isolated particles, dark matter could be more like a plasma, a sea of charged particles
Right.
interacting through this dark force.
Precisely.
Wow.
And this has huge implications for how dark matter behaves. It could clump differently, form structures, even influence the formation of galaxies in ways we haven't even imagined.
So how did the researchers test this idea?
They started by looking at the early universe, just after the Big Bang. They wanted to see if this dark electromagnetism could explain how much dark matter was created in the first place.
So they basically asked, if this dark force exists, would it lead to the amount of dark matter we observe in the universe today?
Exactly.
Right.
And they also had to ensure their calculations didn't mess up what we already know about the early universe. Specifically, they had to make sure their model didn't contradict our understanding of how the first elements formed a process called Big Bang nucleosynthesis,
Right.
or BBN for short.
What did they find? Did their model work?
Amazingly, yes.
Mm-hmm.
With reasonable assumptions about the early universe, their model, with just dark matter particles and dark photons interacting through dark electromagnetism, was able to produce the right amount of dark matter without contradicting our understanding of the early universe. It's a pretty remarkable alignment.
So far, so good. But I imagine it gets more complicated when you start looking at the present-day universe.
You're absolutely right. Things get really interesting when we zoom in on the dynamics of galaxies.
Okay.
The way galaxies rotate and the shapes they form put limits on how strongly dark matter can interact with itself.
Because if dark matter particles were constantly bumping into each other through this dark force, wouldn't it disrupt the structure of galaxies? We wouldn't see the spiral arms and other features we observe.
Precisely. The researchers used the shapes, densities, and the way stars move within galaxies to set limits on the strength of this dark electromagnetism.
What did they learn? Did they find a conflict between their model and how galaxies actually look?
That's where things take a fascinating turn. They found that if dark electromagnetism was the only force responsible for setting the amount of dark matter in the universe, that it would make dark matter too interactive in galaxies.
Okay.
Galaxies wouldn't look the way they do if dark matter was bumping around that much.
So that's a problem, right? It seems like their model is hitting a snag.
It is a challenge, but also an opportunity.
Okay.
This tension points to the possibility that dark matter might have another interaction besides dark electromagnetism. Something else is needed to help set the right amount of dark matter in the early universe without making it too interactive in galaxies today.
So what did they propose? What could this other interaction be?
To solve this puzzle, the researchers considered one of the fundamental forces in our universe, the weak force.
I remember learning about the weak force in school, but I'll be honest, it's a bit fuzzy. Remind me how it fits into the picture.
Think of the weak force as a force that governs certain types of particle decays. It's a bit like a shy character in a play, not as prominent as electromagnetism or gravity, but still crucial to the story.
Okay, that helps. So how does the weak force relate to this dark matter model?
They proposed that the dark matter particle is also a triplet under the weak force. Essentially, this means it has three subtypes, like a coin with three sides. This triplet nature allows for the correct amount of dark matter in the early universe while keeping dark electromagnetism weak enough to avoid disrupting the structure of galaxies.
So we have this intricate interplay of forces. Dark electromagnetism shaping the interactions within the dark matter world.
Right.
The weak force helping to set the right amount of dark matter, and gravity holding it all together on a cosmic scale.
It's a beautifully balanced system, a hidden symphony orchestrating the cosmos. But here's another intriguing twist. This model predicts that dark radiation, those dark photons we talked about, would be incredibly difficult to detect directly.
So it's like a ghost influencing the universe but remaining invisible to our instruments.
Right.
How frustrating. But wait, if we can't directly detect these dark photons, how do we even know they might exist?
That's a great question, and it leads us to the next chapter of this deep dive. While dark photons themselves might be elusive, they could leave behind subtle traces, whispers in the fabric of reality that we might be able to pick up.
Intriguing. So we've laid the groundwork exploring this fascinating idea of dark electromagnetism and its potential role in shaping the universe.
Yeah.
But the mystery deepens. In the next part of our deep dive, we'll delve into the tantalizing question of how we might actually detect these elusive dark photons.
Welcome back to our deep dive into the mysteries of dark matter. Before we ventured into the idea that dark matter might not be just inert particles, but rather a dynamic plasma, a sea of charged particles interacting through this new force we've been calling dark electromagnetism.
And you left us hanging with the tantalizing possibility that this dark matter plasma could be subject to instabilities, kind of like ripples in the fabric of space-time, which could have a huge impact on how galaxies form and evolve.
Right. It's like realizing the ground beneath our feet isn't solid rock, but a constantly shifting sea of sand.
Okay, I'm hooked. Let's dive into these instabilities. What exactly are we talking about here?
Imagine a smooth, uniform halo of dark matter surrounding a galaxy, a giant sphere of these charged particles. In the standard collisionless model, this halo would be relatively static, shaped only by gravity.
But with dark electromagnetism at play, things get much more dynamic and interesting.
Absolutely. Because now these charged dark matter particles are moving around, and their motion can create magnetic fields. And these magnetic fields, in turn, can influence the motion of other particles, leading to a sort of feedback loop.
So it's not just individual particles bouncing around randomly, it's the whole plasma behaving as one entity with its own internal dynamics.
Exactly. And under certain conditions, these dynamics can become unstable. Think of it like a perfectly still pond. If you throw a pebble in, it creates ripples that spread outward, disrupting the smooth surface.
And the Weibel instability is one of these ripples, right? But instead of water, it's the dark matter plasma that's getting disturbed. What exactly triggers this instability in the dark matter world?
The Weibel instability is triggered by something we know happens all the time in the universe, the merging of structures.
So when smaller galaxies collide and merge to form larger ones, or when clumps of dark matter come together, what happens to the dark matter particles?
Those mergers create what's called an anisotropic velocity distribution. It's a fancy way of saying that the dark matter particles end up moving in all sorts of different directions and at different speeds, kind of like a swarm of bees suddenly agitated.
And that's the perfect recipe for the Weibel instability to kick in. So what happens when this instability takes hold? What does it do to the dark matter plasma?
It amplifies magnetic fields. Those tiny initial magnetic fields generated by the moving charges get boosted exponentially, growing stronger and stronger.
Okay, so we've got these amplified magnetic fields coursing through the dark matter plasma. What effect do they have?
Imagine those magnetic fields acting like a sort of friction or viscosity within the plasma. Instead of zipping past each other effortlessly, like in the standard model, the dark matter particles now experience a bit of resistance.
So they start to interact more strongly, exchanging energy and momentum through these amplified magnetic fields. Could this explain some of the puzzles that astronomers have been grappling with when it comes to dark matter?
That's the exciting part. Remember how we talked about discrepancies between the predictions of this standard collisionless dark matter model and the actual shapes of galaxies we observe?
Right. Some galaxies have less dense cores than the simulations predict, while others have more flattened shapes. It's like the dark matter isn't behaving exactly as we expect.
Exactly. And dark electromagnetism, with its associated plasma instabilities, might provide the missing piece of the puzzle.
I'm all ears. How could these instabilities explain what we see in galaxies?
Well, that increased interaction caused by the amplified magnetic fields can smooth out those overly dense cores, making them less concentrated and more in line with observations.
So it's like the magnetic fields are acting like a cosmic blender, smoothing out the clumps of dark matter in the centers of galaxies. What about the flattened shapes of some galaxies? Could that be explained too?
That's also a possibility. The influence of these magnetic fields could shape the distribution of dark matter in ways that gravity alone can't, leading to those more flattened structures we observe. It's like adding a new force to the cosmic sculptor's toolkit.
It's mind-blowing to think that this invisible world of dark matter might be so much more dynamic and complex than we ever imagined. But I have to ask, how do we know for sure that these plasma instabilities are really happening? It all sounds very theoretical.
You're right to be skeptical. The researchers acknowledge that fully understanding these plasma instabilities requires very sophisticated computer simulations, which were beyond the scope of their initial paper.
So it's like opening a door to a new room, but not quite stepping inside yet. We need more powerful tools to explore this new landscape.
Precisely. But even this glimpse is enough to spark our imaginations and fuel our curiosity. It's a reminder that the universe is full of surprises, that the dark sector might be teeming with activity and complexity just waiting to be uncovered.
This is also fascinating, but I keep coming back to the question of how we can actually detect these dark photons if they interact so weakly with ordinary matter. They're like ghosts passing through our detectors unnoticed. How do we even begin to search for something so elusive?
That's the million-dollar question, isn't it? How do we hunt for ghosts? But even ghosts leave traces, subtle whispers in the fabric of reality, and scientists are devising some incredibly ingenious methods to try and pick up those whispers.
Okay, now you've really got my attention. In the final part of our deep dive, let's explore these ghost hunting techniques. What are some of the ways scientists are trying to catch these elusive dark photons? Welcome back, fellow explorers. We've been on quite a journey through the shadowy realm of dark matter, haven't we? We've gone from the basics to some truly mind-bending possibilities.
We've considered the idea that dark matter might not just be some passive stuff, but rather a sea of charged particles interacting through a hidden force, dark electromagnetism. We've even explored how this could lead to instabilities in the dark matter, plasma, potentially influencing the very structure of galaxies.
And we ended on a real cliffhanger, the question of how we could actually detect these elusive dark photons, the carriers of this dark electromagnetism. They're like ghosts, practically invisible to our instruments.
Right.
So where do we even begin to search for something so elusive?
That's the challenge, isn't it? It's like trying to find a needle in a cosmic haystack, a needle that's also invisible. But even ghosts leave traces, subtle signs of their presence.
Right.
And scientists are coming up with incredibly clever ways to try and find those traces.
So spill the beans. What are some of these ghost hunting techniques? How do we track down something that barely interacts with our world?
One approach is to look for tiny variations in the electromagnetic field. Remember, electromagnetism is the force that governs light, electricity, and magnetism in our everyday world.
So it's like listening for a whisper in a room full of noise, a faint signal amidst the background hum of the universe.
Exactly. Experiments like ADMX are doing just that. They're essentially searching for faint oscillations in a strong magnetic field. The idea is that on very rare occasions, a dark photon might convert into a regular photon, a particle of light, which we can detect.
It's like waiting for that one fleeting moment when the ghost reveals itself, a whisper turning into a shout.
Another approach is to search for missing energy in particle collisions.
Missing energy? How do you lose energy in a particle collision? It's not like it just disappears.
Right. Energy can't be created or destroyed, but it can change forms.
Okay.
And that's the key here. If dark photons are produced in these collisions, they would carry away some energy and momentum, but because they interact so weakly with our world, they'd escape the detectors unnoticed.
So it's like a magic trick where something vanishes into thin air, but in this case, the magician is the dark photon.
Exactly. Experiments at the Large Hadron Collider are meticulously measuring the energy and momentum of particles before and after a collision. If they find a discrepancy, some missing energy that can't be accounted for, it could be a sign that dark photons were produced and slipped away unseen.
It's detective work on a cosmic scale, piecing together clues to track down the invisible culprit. But it sounds like finding these dark photons is a real long shot. Are there any other strategies scientists are exploring?
Absolutely. The search goes beyond Earth-based experiments. Astronomers are also looking for clues in the cosmic microwave background radiation, the afterglow of the Big Bang.
That's the faint light that has been traveling through the universe for billions of years, carrying information about the early universe, right?
Exactly. And if dark photons existed in the early universe, they could have left subtle imprints on this ancient light.
So the universe itself becomes a giant detector, preserving clues from the dawn of time. What an amazing thought.
It really is. It's a testament to human ingenuity, our drive to understand the universe, that we're finding ways to probe realms that were once thought completely inaccessible.
It's humbling to think that we're only just beginning to scratch the surface of what's out there, that the universe is filled with wonders we haven't even imagined yet.
And that's what makes this journey so exciting. Who knows what mysteries await us in the dark sector? Perhaps one day, through these ingenious experiments and observations, we'll finally catch a glimpse of those elusive dark photons, revealing a hidden universe and revolutionizing our understanding of the cosmos.
It's a thought that sparks both excitement and wonder. We've taken a deep dive into a realm once thought to be completely dark and inert, and we've found hints of a world teeming with activity and complexity. We've explored the possibility of dark matter having its own forces and interactions shaping the universe in ways we're only beginning to comprehend.
And while the hunt for dark photons continues, the very act of searching, of pushing the boundaries of our knowledge, is a testament to the power of human curiosity and a relentless pursuit of understanding the cosmos. So as we conclude our deep dive, let the mystery linger. Let it fuel your curiosity, inspire you to ask questions, and perhaps one day you'll be the one to unravel the secrets of the unseen universe. Keep exploring, keep questioning, and who knows what wonders you might find